Welcome back. Now let us deal with a Boolean ring. The definition is like this. A ring R is a Boolean ring if A square is equal to A for all A belonging to R. We all know A square is equal to A means element A is idempotent. So what is a Boolean ring? A ring in which every element is an idempotent. We will call it as a Boolean ring. Now the question here asks you to show that every Boolean ring is commutative. We want to show that every Boolean ring is commutative. So what I mean by commutativity, A into B is the same as B into A. I want to show A into B is the same as B into A. So let us start with A into B. But A itself is A square and B is B square. So what will happen? This will be A into B into B. And this being a ring, multiplication is associative, you know very well. At the same time, it is commutative also. I'm sorry, we want to show that it is commutative. I'm sorry, we want to show it. But we want to use the idempotency of this particular. So what do we get over here? A as it is. And this will be AB. Into B. So what we are saying? No, this will not work. So how will you go? We want to use idempotency for commutativity. So AB is nothing but A square into B square. That's the thing with us. So what we can do is, this is nothing but AB. So let us use the yes, would you try? Please try in your notebooks. What we want to show is AB comes out to be BA. How will you proceed? This is our requirement. What we have is, it's a Boolean ring, means every element is idempotent. That is the only knowledge with us. And we want to show that the multiplication proves to be commutative here. So how would you go? AB is A square B square. So I can make use of this. I can go with the associativity. What else I can do? Have to reach to AB is equal to BA. Anyone? Priya, you have tried for your presentation. I think you forgot. That's what I wanted from you. AB, is an element in the ring. It is also idempotent. So I can write AB as what? AB multiplied by AB, isn't it? To this side, what should I have? AB multiplied to AB. Are you getting this? I just waited for your answer. See, what fact I made use of here? AB I can write as A square into B square. So I used A into A multiplied by B into B. I used associativity twice and I got this to be A into bracket AB into B. Now the left side was AB and you know it is also an idempotent, so it will be AB into AB itself. So these two sides are equal. Let me use once again associativity over here. So what this will give me? A multiplied inside by BA and multiplied by B out. Can I say so? And right side will be A into AB multiplied outside by B. What we have to do is repeatedly we have to go for associativity. And now you can see left cancellation law, right cancellation law. And what is the result in your hands? BA is equal to AB. Got it? Okay. I would like to once again explain the fact to you. What I did was A into B, I wrote as A square into B square. Why for? Because A is idempotent, B itself is idempotent. So I can do so. Further, I used associativity to the right hand side twice. And I got this to be A into AB into B. Now to the left side, AB itself is idempotent, means AB whole bracket square is AB itself. So the left hand side I have expanded this way, AB into AB. Are you following me? And then what we did was here also again we used associativity twice and then we used our cancellation laws, left as well as right. If not understood, I would like to once again go for CR. I would like to help you. See, AB, we said it is A square into B square. Okay. Because only one hand I got, one thumb. Okay, doesn't matter. Now I'll write it as what? A square I can expand as A into A. Feel all of you agree? B square I can write as B into B. So that is what I have done. Now let me use the associativity. So one A is left over here and this A let me combine with B into B. So once I used associativity for multiplication. Again, I would like to use associativity second time. So A and B combined and B as it is. This is what we are saying. I feel you got me. So this was the way we dealt with it. So this was AB. Assuming A is idempotent, B is idempotent, I reach to this. Now next time what I'll do is, I'll say product AB itself is idempotent. So product AB is idempotent means what is going to happen? AB can be written as AB into AB. Again, you use associativity twice. So A kept as it is in the bracket. I have engaged this B here. Nowhere we are changing order, only we are using the property of associativity. So what do I get over here? Inside BA into B. And now both are the values of AB. So we have to equate them. A inside I got AB times B and right side is A into BA times B. Hope you follow me. Now what I watch is to the left side. I have got A. So left cancellation law helps me in cancelling it. Now I'm just left with AB, bracket close, into B, and this side I have BA into B. Followed? Now what will work here? Obviously, right cancellation law. So B is getting cancelled. And what is your result? AB is equal to BA. What is the result? AB is equal to BA. Followed? So I think only you have used idempotent property. So I'll say idempotency. And from that, you could show that multiplication is commutative. So the ring becomes commutative ring. Okay. So hope it was so simple. So follow the thing. All right. So what we have shown over here, a Boolean ring is always commutative. A Boolean ring is always commutative. All right. Now I would like to proceed for the next example, which is a part of your practical. So a set S is given. Let power set of S be the collection of all subsets of S. So very well you are familiar with the power set of S. I would like to take this question with us over here. Okay. So all of you are watching. We are going to deal with the power set of S. Now, capital A and capital B are members of the power set. Have to add the elements A and B. A plus B means A union B minus A intersection B. From the union, we are just deleting the intersection part. Means what? X will be either in A but not in B, or in B but not in A. Likewise. And how to define multiplication? Multiplication is the intersection part. So with these operations, they are asking us to prepare tables for addition and multiplication. And the set given to us is a very small set with two elements. So I think all of you remember what is meant by a power set. See here, S contains only two elements, A and B. So what is the power set of S? Yes, it contains empty set, then singleton A, then singleton B, and the whole set AB. Either you call it as S or just write it AB. So how would you define phi plus singleton A? So how is the definition? Whenever you are adding two sets, what is the definition given to you? Take the union and from that you subtract the intersection. So intersection will be empty. So very naturally, what is the addition over here? Addition will be singleton A. Okay, so it's better. Let us have a kind of table with us. I would like to go with a table. I think you got the concept. So what we'll do is let's have a kind of table for addition. So I have empty set. I have singleton A. May I denote it as only A? or it's better. Let us go with, and this is set S itself. Here again I have phi, singleton A, singleton B, and lastly let me write S. Now you will help me in writing out the, okay, phi plus any set. Phi plus phi is going to be phi because there is nothing in it. If I, yes, of course I'm writing for plus. This is going to be singleton A, just now you saw. The same will work with singleton B, and the same is going to work with S. I feel so. Have you got this concept? What I have done? What I have done? I have taken union of the sets, and from that I have subtracted the intersection. Because it is intersection with phi, intersection will be empty. So no need to worry about it. Okay. Now let us go with singleton A with phi. It has to be singleton A only. So vertically also let us write down the same kind of thing. And talking of S also, you will get the same result. Okay. Now I would like to go with this singleton A. A union A is A minus intersection. So this has to be empty. Do you agree?
Yes, ma'am.
Okay. What we are doing, singleton A union itself is singleton A. And from that we are subtracting their intersection. Intersection is also singleton A. So the same set subtracted from itself. What is left? Empty set. Okay. What about singleton A union B? So it is going to be AB. And from that, you are subtracting the intersection. So you are subtracting phi, means this set is going to be S. Am I right? What I did first, I took the union. A and B, union is AB. And from that, I subtracted their intersection. What is their intersection? Empty set. So I got complete set S over here. Now let me talk about the last. A and S. What is the union? A and S. What is the union complete? S. And what is their intersection? Singleton A. Intersection of S and singleton A is singleton A. And if I subtract it, what I'm left with? Singleton B. Do you agree? If not, I would like to go here once again. And what I'll write here is the union is AB. And from that, I'm just subtracting singleton set A. So what I'm left with? Set singleton B. Is it fine? Okay, only 2 thumbs, I got 3. All right. Now, I would like to move next for the next row. Next row contains singleton B. Now, the union of B with phi, the union of B with phi, and intersection is phi. So, naturally, it is going to be singleton B. Now, I take union of B with A. So, this is going to give me A comma B. And from that, I'm subtracting singleton B. So, what I'm left with? No. What should I subtract? Come up. Intersection of B and A, phi A. Yes, I'm subtracting phi. So what is the answer here? S. Okay. Now let me take the union of B with B. I got singleton B. and I need to subtract the intersection of B with B is again B. So what is the answer? Singleton B minus singleton B. Pi. It's empty set. And lastly, if I take the union of B with S, I will get whole of S. My S is AB. And from that, I'm subtracting the intersection. Intersection is singleton B. So what I'm left with?
Singleton.
Singleton A. Okay. And now the last row, that is S. So as far as S and phi are concerned, the answer is ready with us. Now
Singleton B.
we want to proceed. S union singleton A is whole of S. From that, I subtract S intersection A, means singleton A. So what I'm left with?
B.
Yes. Similarly, you take union of S with B, that is AB. And from that, you are subtracting the intersection. What is the intersection? Singleton B you subtract. So what is the answer with you?
A.
Yes. And lastly, S union S is S. S intersection S is S. And the subtraction will be empty set.
Phi.
Yes. So this is what we are expected to do. So I feel you got it. So this was the addition table. Now you are required to form multiplication table. So let us go for multiplication table. How the multiplication is defined? Multiplication is simply intersection. So I think that will be quite easy for us. So let us go for multiplication. We have 5 as our first set, singleton A. Then I'll have singleton B. And lastly, we have S. Here also we have 5, singleton A. Then we have B. And lastly, S. I think all of you are ready with the answer. We are continuing with multiplication. Okay. So I hope you'll help me with the first row. The intersection of 5 with 5 is?
Phi.
With singleton A is?
Singleton.
9. 5 intersection.
Phi.
We are taking intersection. Never forget. It is completely 5. Okay. Vertically also, you'll get it to be 5. Okay. Now let us go to the second row. Yes. Singleton A with singleton A. Got it? Yes. A with B we got 5. Yes. And A with S we got
A.
A. Now for B. Come up.
Phi.
Yes. First thing is 5. Next is also 5.
Second. B.
Here it is singleton B. And lastly,
D.
yes,
B.
singleton B. And talking of S now,
A.
yes, yes. Next is,
Singleton B.
yes,
S.
S itself,
S.
yes. So what you observe, every element if you see, A into A is A, B into B is B, S into S is S, and phi into phi is again phi. So every element is an idempotent. Got the thing? So you got this ring to be idempotent. One more thing, if I have diagonal over here, let me have a kind of diagonal over here. This is a, sorry, this is our diagonal. So do you observe there is symmetry?
No.
Huh? I think you observe symmetry over here. This element you can see over here, same element. Then this element you will observe over here, and at the same time here also.
Yes.
Lastly, you can say this is phi, this is phi, this is singleton A, this is singleton A, and B, B. So you are observing that.
Commutative.
Yes, it is commutative. So we have just now shown that Boolean ring is always commutative. So same you have observed here. So this question is from your practicals. I hope you can write this. Okay. So what you observe, we have shown a bit. We have found out the tables for addition and multiplication. And next B part, we have shown that it is a Boolean ring. Fine. Is this okay? Can I proceed? All right. All right. Now I would like to move to this example. It's very interesting for you. See, you are required to solve the equation x square minus 5x plus 6 equal to 0. See, whenever we solve, yeah, it is solved over here. So I would like to go with this. X minus 2 into x minus 3 will work over here. And we know that we say x is 2 or x is 3. That is our answer in integers. But now we are in integers modulo 12. Means whenever the number divided by 12 leaves whatever remainder is your answer. So see over here. In Z12, what are the zeros? All multiples of 12, they are zeros. So let us see what happens. 2 6s are 12 is a 0. 6 2s are is a 0. 4 3s are is a 0. 3 4s are is 0. 3 8s are 24 is a 0. 8 3s are is also 0. So these many zeros we have written over here. 4 6 are, 6 4s are, 4 9s are, 9 4s are, 6 6 are, 6 8s are, 8 6 are. I hope all of you are observing, all of them, they are divisible by 12. So these many zeros, I mean these many zero divisors you can say, because their product is 0. So we will call them as divisors of 0. So if I solve this kind of equation in Z12, what is my answer? 2 and 3 is a pair, one of the pairs. But you can see 6 is also the answer. Okay. Now you can see if you take 6 minus 2 into 6 minus 3, that gives you a 0. Or else you take 11 minus 2. What I'm doing, I'm using this factorization. And here I'm putting the values of x. From where I've taken values of x? From Z12. You know better, the members of Z12 are 0, 1, 2, 3 up to
11.
yes, up to 11. So I have taken 11. 11 minus 2 into 11 minus 3. That also produces a 0 in Z12. So what is the solution of this in Z12? You are observing 2, 3, they are themselves solutions, no doubt. But these many factors you observe. And if you are able to give such kind of factors over here, that is your solution. So you can say 8 into 6. When you'll get 8 into 6 over here? When to get 8? What minus 2 is 8? 10 minus 2 is 8. What minus 3 will give you 6? 9 minus
9.
2. So that way you'll get the values of x over here. Sure? I suppose you are getting my point. So this way you can get the values of x from Z12. Why? Yes, Pradnya, I am not able to hear you.
Nothing, ma'am.
Okay, okay, okay. Now I would like to go to this definition for the same. That was my purpose of giving that example. See, A and B are two non-zero elements of ring R, and still we observe that product AB is zero. Up till now, before learning rings, we had an impression that whenever I multiply by zero, then and then only I'll get the answer to be zero. But in rings, what you observe here, there are two non-zero elements and their product becomes zero. Then A and B will be called as divisors of zero. A and B are called as divisors of zero. So here you have observed, what are the divisors of zero? 2 and 6 are divisors of 0 in Z12. 3 and 4 are divisors of 0 in Z12. 6 and 8 are divisors of 0 in Z12. Likewise, so many divisors you can watch over here. Okay. So what I mean by divisors of 0, the numbers themselves are non-zero elements. Still their product becomes 0 in that ring. Then such numbers are called as zero divisors or divisors of 0. Followed the fact?
Yes, ma'am.
So very directly I can say a ring with 0 divisors. I'll be calling the ring as ring with 0 divisors. So let us go with one theorem over here. Obviously, such kind of thing will occur in Z suffix n. What is Zn? Residues modulo n. Okay. The set of all residues modulo n. In the ring Zn, the divisors of 0 are precisely those non-zero elements that are not relatively prime to n. So for this, before going to the proof, I would like to deal with a table of Z6, which we are quite familiar with. Many a times we have used it, and I think that's a favorite one. So let's have Z6 with us. 0, 1, 2, 3, 4 and 5. We are to prepare a multiplication table because we want product to be 0. If I multiply by 0, the row becomes 0, so I won't write it. I'm not interested. I'll go with 1. So hope you'll prompt me easily. Come on. 1 1's a 1, 1 2's a 2, 1 3's a 3, 1 4's a 4, 1 5's a 5. I hope you'll not forget we are in Z6. So multiplication modulo 6 you are telling me. 2 1's are 2, 2 2's are 4, 2 3